In today's lesson, we are going to be looking at the transformation of sine waves. So this will be a summary of the Desmos investigation you would have done in the previous lesson. I'm just going to go through and summarize what you should have found. So similar to when we looked at the transformations of quadratics, we have a general form or general equation that we're going to use when we're applying our transformations. Basically, we're just going to fill in the blanks with whatever the transformations are. So our general function or general form for the sine wave should look something like this. F at x equals a sine of x minus c plus d. Now you might notice that this is very similar to our quadratic general form, and that coincidence or that similarity will transfer over to what the transformations are as well, just obviously with a different base form. So we're going to look through what the A, C, and D value represent in terms of transformations. We already made guesses or hypotheses on what these values would do based on what we know about the quadratic transformations. And again, we'll find that we're not too far off. So looking first at the A value. So we have our base form in black, f at x equals sine x. And then we have the two other forms, 2 sine x and 1/2 sine x in red and blue. So taking a look at them, what do we notice is different about the red and the blue graph compared to the black one? What do we notice? We might notice that they all still cross at the same values, right? The max and the mins are at the same horizontal axis, but we might notice that the max and min aren't in the same spots. Some are higher and some are lower. In the next one, looking at the A value, we have the black graph again showing our f at x equals sine x, our base form. Then we see the red is negative sine x, and then the blue is negative 3 sine x. So what is changing between these? There is something different. It might be hard to see when we have all three, but if we were to able to kind of make some disappear and then reappear, hopefully we'd be able to see the difference. And if you made the comparison to the quadratic transformation, you would find that we have something similar. So when A is greater than 1, we have what we call, again, a vertical stretch. Right, so again, that's making it narrow or taller. I'm going to say taller in this case, taller. It's not really making our sine wave narrower. It's making it taller. When A is between 0 and 1, we have again a vertical compression. And it's going to make it shorter. When A is negative, again, we have that reflection. In the x-axis. Or we could say it's flipped. Now the key thing, how to really find this, is that the A value is the amplitude. So if you go back and look at those examples, you'll find that whatever the amplitude is, that is what the A value is. Right? So the A value you can determine by the amplitude. Again, remember the amplitude is always positive, so we have to look for a reflection or a flip in terms or to determine what the sign is. But for the actual value, we just have to find the amplitude, which we've looked at in previous lessons. Moving on to the C value. We have our base form f at x equals sine x in black, and we have two different ones in blue and in red. So how have these graphs changed, the blue and the red ones? You still have the same kind of general form. They're still crossing the x-axis at the same 90 intervals. However, if I look at just highlight some points like the maximums, they're all in different spots. And they're not higher or lower like when we looked at the A value. They're left and right. So the C value When C is positive, you could say you have a horizontal translation right. You could also say shift right. You could also say or shift right, or you could say phase shift. So again, just some different terminology. When C is negative, we have a horizontal translation left. And again, we can refer to it as a shift left or a phase shift left. Now, how to find this? This one might look a little bit difficult because of the way the graphs appear. However, the key thing is always look for that starting point. Right? We want to look for 0, 0. Right? 0, 0 is where we should be starting. If it's changed anywhere from that, right, then we know that there's a phase shift left or right. We could also look for the maximum and the minimum. We could say our first maximum should be at 90 and 1. So if it's shifted anything from there, in terms of anywhere, in terms of 90, then we know we have a phase shift. The D value, okay, this one should be relatively obvious. Again, looking at our graph, in our base form in black, sine x, and we see sine x plus 2 in red, sine x minus 3 in blue. In this case, again, similar to what we did before with the D value or the K value, when D is positive, we have a vertical translation up. When it's negative, vertical translation down. Now, this could also be found by drawing the midline. Right, the midline, the equation of the axis. If we can find the midline, we can find what our D value is. If I go back and look at these, I see my midline here is at -3. That's also what my D value is. In red, I can see my midline is 2, or I could calculate that, and I see that my D value is 2. So there are some ways to make it easier to find what these values are. One other thing to note, the D, similar to the quadratic transformation, the D value is exactly as we see it. The C value, it's opposite of what we see. Right? So if C is positive in the equation, it will look negative. And same with if it's negative, it'll look positive. So again, those are the 3 transformations that we're going to be looking at in terms of the sine wave. And you'll see that they're very similar to, if not identical to, the transformations in the quadratic. So it makes it really easy to remember what they are. When looking at graphs or when trying to find the transformations from a graph, we do have some key characteristics that we can look for, such as the amplitude or the midline, which will make it easier to find like the C or the A and the D value. Similar to how in the quadratic equation, we had the vertex to look at and the step pattern, same kind of idea with the sine wave. We have some characteristics of the sine wave that we can use to help us find these values. So looking at the base form, this is our base form of our sine wave. And again, this is going to be helpful in finding what the transformations are, or drawing the transformations, or coming up with the transformations. Whether we're looking at a graph, again, remember everything's spaced out equally by 90 degree intervals. We should be starting at 0, 0, right? And then at 90, it's 1, another 90, we're back at 0, another 90, we're at -1, another 90, we're back at 0. So that's always going to be kind of the base form that we should be looking for. The amplitude in our base form is 1, or you could say the A value equals 1. The period is always going to be 360. We didn't really talk about any transformations in that sense, so we don't have to worry too much about that. The equation of the axis is going to be 0. This is also the same thing as saying our D value equals 0. And then in our general form as well, because there is no shift left or right, our C value will be 0 as well. So in our general form, our A is 1, our D is 0, and our C is 0. Again, identical to the quadratics. So let's just go through some examples, again, of trying to describe the transformation of the following graphs from our base form. So first one, we have g at x equals negative, or sorry, not negative, 1 over 2 times sine of x minus 180. So in this case, we have an A value of a half and a C value of 180. Again, opposite of what we see. The A value tells me, because it's a fraction, it's between 0 and 1. Vertical compression by a factor of 1/2. You could also just say amplitude of 1/2. And the C value of positive 180 means a phase shift right 180. So we've moved our entire graph over 180. Now with the sine wave, it may not appear like it's actually moved at all. If we're going from like in terms of negative infinity to positive infinity, right? Seeing how that sine wave goes on forever, there may be some shifts where it doesn't really make any difference. But if we're looking at just a single sine wave, yes, it would appear that there's a difference. In B, our A value is negative 2. We don't have a C value, and our D value is 4. So because it's negative 2, we could say, focusing on the 2, could say amplitude of 2. The negative means a reflection in the x-axis. You could also say flipped. The D value of 4 tells us vertical translation up 4. We could also say a midline of 4, right? So showing us that we have a new midline. The second example, doing the same thing except going from an equation or from the word transformations to the actual equation. So again, we're using that general form, f at x equals a sine of x minus c plus d. So we just need to figure out what these transformations represent. Amplitude of 4, a is 4. Vertical translation down 3 units means my d value is negative 3. And a phase shift of right 270 degrees means my C value is 270. Now I just need to plug these into my general equation. F at x equals 4 sine of x minus 270 plus, or not plus, minus 3. For B, same idea. Look at the different transformations and apply it to the specific value. Phase shift left 90 degrees. So C value equals negative 90 because it's left. Reflection in the x-axis and the amplitude, that is going to both refer to the A value. Reflection means it's negative. Amplitude of 0.25 means the A value is 0.25. So F at x equals negative 0.25 sine of x. You could say minus negative 90, but when you subtract a negative, it becomes plus 90, and then we don't have a D value to worry about. The next example, now we're going to determine the transformations from that base form and then write an equation. So sometimes it's helpful if we get, again, an understanding of what the base form should look like. So if we need to draw it in, we can. So 0, 0, 91, 180, 0, 270 and 1, 360 and 0. So this is our general form. I'll actually do it in red, make it a little different. How has our graph changed? Well, we can see that it's clearly shifted down. We've shifted down to negative 3.5. So you can say vertical translation down 3.5. Has our amplitude changed? Well, if we look at our amplitude, no, it looks like it's still 1 because we go from 3.5, negative 3.5 to negative 2.5. So that's an amplitude of 1. Do we have a different starting value? In this case, no, we start at 0, 0. Or in this case, it's 0, negative 4, but we do start on the y-axis. And then we have our main points at the same spot. So there is no shift left or right. The same graph, just shifted down. So in this case, we only have to worry about a vertical translation of down 3.5, which means that we have a d value of negative 3.5. So our graph will be f at x equals sine x minus 3.5. For b, again, if it helps, draw in your base sine wave. So 0, 0, 90 and 1, 180, 0, 270, negative 1, and 360. So this is our graph. We can clearly see that it's not starting at, our new graph is not starting at 0, 0. It's actually starting here at negative 550. So this means we have a phase shift left of 500 or 150. I think I said 550, but I meant 150. The amplitude is still 1, the midline is still 0, so I haven't shifted left or right or up or down. So this is my only transformation. So in this case, my graph or my equation would be f at x equals sine of x, and then because it's left, I'm going to put the opposite, so plus 150. Now, there could be another way that you write it, because if you look, you do see a point at this midline over here as well. So if we knew what that exact value was, because this one's at 30 or 150, negative 150, I'm probably guessing this is at 210. Right, just kind of off by 30 or overall. So I could adjust that, or if I knew that actual value, I could actually put it as a phase shift right, whatever that value is. But because I don't know for sure, I'm just going to use the value that they give me. But in some cases, depending on what we have, you could have different phase shifts. You could be either shifting left or you could be shifting right, depending on what the graph, or depending on how you see it. Lastly, now we're going to sketch one cycle of the following sine waves. In this case, f at x equals 2 sine of x minus 90 plus 1. So I have my original sine wave in here just as a reference, because sometimes it's helpful to draw the original and then make all the changes. So we know we have an amplitude of 2. I'm not going to worry too much about that. I want to know where I'm starting, because then from there I can go out to each point. So I'm shifting to the right, phase shift or shift right 90, and I'm going to shift up 1, and the A value tells me I have an amplitude of 2. I'm going to focus on the shifting left and right first, or the right and up first. So this one point here, I'm going to go over 90. So my new graph is going to go over 90 and up 1. So my new graph is going to start there. Now this is where the 5 key points come into play. Because each point is at an interval of 90, I know that my maximum should be at this horizontal distance. Right? Same way we start here, our maximum was at 90 away. So it's the same idea. So if I start here, my maximum should be somewhere along this kind of invisible vertical line. And because I have an amplitude of 2, that means it should be up 2 from this midline or this starting value. Then another 90 away, if I look back to the base form, I come back to that midline. And then another 90 away, I go down to my minimum. So again, imaginary vertical line, somewhere along this point, 90 degrees away or 90 units away to the right, I should have my minimum. Again, the amplitude is 2, so that tells me that the minimum should be down 2 from this midline here. And then again, another 90 units, and I come back up to 0. So in this case, if I want to sketch this graph, it looks something like that. So that's one cycle of the sine wave 2 sine of x minus 90 plus 1. Next, we're going to do the same thing. Look for the transformations and then sketch the following. However, we're not going to have the original there to help us. So let's figure out our changes first. In this case, the negative in front of the sign, we have a reflection or a flip in the x-axis. No c values, no left or right, but we do have a d value of -3, so a shift down 3. So again, I know if it helps, you can always draw in your base form. Right, again, equal intervals of 90, amplitude of 1, starting at 0, 0. So for my new one, I'm shifting everything down 3. So I'm going down to 3. There's no left or right, so this is where I'm starting. However, it does say that there's a reflection in the x-axis. So that means that I'm flipping my graph. I'm flipping everything. So for my next one, because in my original form, I go up to my maximum, in this new form, I'm going to go down to my minimum first. I'm still going to come up to 0, and then I'm going to go to my maximum instead, and then come back to 0. So it's almost like a mirror image of our sine wave or our base form, right? When we flip it, the first maximum becomes a minimum, the first minimum becomes a maximum. The midpoints don't change, or that the points on the midline don't change because you're at 0 or you're at the line where you are essentially flipping it anyways. So this would, in red, this would be our new graph or new sine wave. And again, this is only one cycle. You could continue this cycle on. But the main thing from this lesson is just understanding, again, what the values represent in terms of transformations, seeing how similar they are to the quadratic transformations, and then just being able to recognize the transformations or come up with the equations or even the graphs depending on the information given.